So what I will do today is just a brief general introduction to the concept in thermodynamics about cycles. Okay, so briefly speaking, so let's just pick a pen. Yeah, sorry. And this one, a cycle in thermodynamics can be seen in a diagram. Thermodynamics um, is really well studied with diagrams. You can see the processes and the states. And let's take, for example, one here. So then it comes to the state two by some process, okay? Adiabatic, maybe, isothermal, maybe, I don't know. Isobaric, whichever. It doesn't really matter those details right now. And then it goes to three, and then maybe to four, okay? And then it goes up to one again. So what you see here, this is exactly the diagram of a cycle. And the thing is to go all over the same states over and over again. One and two and three times and four times. So this is actually the concept of a cycle, which is a sequence. Let me just put it, sequence of a process, I would say of processes where the final state equals initial state. Okay, so this is just the wording of what you have here at your right, here in this diagram. Okay, it doesn't really matter which axes are the diagrams. The thing is that whenever you have a process that goes over again, I mean a set of processes that goes over and over and over and over again, well, you are in the presence of a cycle. So this is just what a cycle is. And in thermodynamics, we use them a lot. Why? Because they are useful. These things are actually really useful because, for example, if you get this area over here, it actually depends on which axis. Now it depends on that. But if you get this area over here, then you will be able to calculate something we know as work. Okay, so that is actually pretty important as you know, in thermodynamics. Well, okay, so that's the general view. Now, cycles, I'm gonna do this, okay? So forgive me because I want to use more space. And that thing that I just put over here, it's important, but it's not that relevant. But it's relevant, I think, for this, at least for this video, is what I'm gonna put over here. So let me just start and use the red one, okay? So it's like more dramatic. What you want here, let me just change to here. Oh, well, it doesn't make, I thought it was gonna be a huge difference from the 0.35 to the 0.5, well, whatever. The idea for a cycle, for one type of cycle, is to take some heat out of a high temperature reservoir. So this rectangle over here is just a way to, the schematics of a high temperature reservoir. You extract some heat from that heat at high temperature from that high temperature reservoir. You put it into a machine or a set of devices, which is called overall heat engine. That's the way it's called, okay? So heat engine because it works on taking heat from somewhere. It produces work, and then it releases heat to a low temperature reservoir, So it's not that hard, at least to schematically understand this. Here inside could be a car engine, okay? So a car engine, what it does, it takes heat from somewhere. It actually takes it from the fuel, from the combustion of a fuel, and then it produces something useful, which is the turning of a crankshaft, or you want to put it, or the movement of the piston, or whatever. But that means that it produces work, and it releases heat into a low temperature reservoir. For example, this thing is not just something really metaphysical or something. This is actually something that is real. This thing, you could call it combustion, the combustion chamber. And this thing over here is something actually pretty real, which could be a lake. A lake? Yeah. like nuclear reactors or something, or maybe the atmosphere. So I'm just gonna put that, or the atmosphere, or maybe the ocean. Maybe you use the ocean as a heat dump, somewhere to place the disposal of heat that you are not using. Oh, okay. So this is actually what it happens to to this to a power plant. A power plant takes heat from somewhere. I told you about a car engine, but it could also be the same schematics for a power plant. It takes heat from a boiler, then it produces work at the turbine, and then it releases heat at something that we call condenser, but it's just a heat exchanger, okay? So this is what we have over here. This is the schematics of a power cycle. Power cycle. So it's a cycle intended to produce power. In this case, this is a useful effect. Okay, so let me now use something called first law. So the first law, hopefully by this time of the course, you already know what the first law. And if you don't, maybe you remember, which is delta U equals to Q plus W. Okay, not that difficult. This is the typical way to put it for a closed system. Well, notice this. I'm doing the analysis for this heat engine, and this heat engine can be as complicated or sophisticated as you want, but if you see here, you don't have mass flows or into or out of this heat engine. You just see energy transfer as work or as heat, okay? Therefore, that's why I'm putting for a closed system. It's not an open system, okay? Okay, fine. Now, there's also one catch. This catch is this one. So this thing is zero. Why is delta of the internal energy, the difference in the internal energy, is zero? Well, just because of this. So I need to be more explicit about it, but I would say that after a cycle, delta T equals zero, delta U equals zero, delta P equals zero, or whichever delta of a property volume equals to zero. They need to be zero. Why? Because you go to the same place. Okay, so you were here at 1, and then 2, and then 3, and then 4, but you get to the same place. So this first law that I'm writing over here is I'm putting after a cycle, or maybe 1,000 cycles. It doesn't really matter, but it needs to be an integer number, and then you get to the same place. 1, 2, 3, okay? So you go to the same place. So after a cycle, you are at the same state. If you are at the same state, you cannot say that there's a difference of anything, okay? You don't have a temperature difference, you don't have an internal energy difference, you don't have a pressure difference. You are right here at the same spot. It's like cheating. Well, no, it's actually doing the first law after a cycle has passed, okay, has happened. So we want to analyze what has happened after a cycle. Well, you see that this delta U equals to 0, but Q plus W stays. Okay, so let's just analyze that. 0 equals to Q, but there are two Q's here. One that goes in, that's a positive, minus one that goes out, which is the QL, minus the W, which is also getting out from that, from the heat engine. Therefore, what I'm gonna do is some algebra, really complicated algebra. I'm just joking, because this is pretty simple to see, minus QL. Okay, so this is your first law conclusion. Okay, so you have a first law, you do this, and maybe you see that if you want more work, then QH needs to be as high as possible and QL needs to be as low as possible. And if you can do that, you will be producing more work than other car or power plant or whatever. Okay, so that's what you got from the first law. Now let's use the second law. Oh, the second law, I have forgot about it. Well, do not, because we're gonna use it. So Q divided by T plus S gen. Hopefully you remember each one of these terms. This is the change in a property called entropy, which is gonna be 0 after a cycle. Oh, okay, so yeah, as this one, yeah, as that one. Now, what about Q divided by T? Well, there are two Q divided by T. One of them is QH divided by TH, and the other one is QL divided by TL. That's entropy transfer going in the system, which is the heat engine, and going out of the system. So I'm gonna put 0 equals to QH divided by TH going in, that's entropy going in, minus entropy going out, TL, plus Sgen, okay? So what I'm gonna do is I'm gonna put in explicit form. Now, I'm not trying to solve anything here. I'm just discussing what's happening to these types of processes here, which we call cycles, okay? So Sgen, which is the entropy generation. Remember, this is the big line of the second law that somehow it goes poof and something happens to the energy sources. We have a set of videos regarding this term, okay? It's a really difficult, or maybe it has some shady physical meaning that is actually really difficult to grasp. But we can make an effort in order to understand that. So Sgen equals to, I'm gonna put this guy over here, therefore I'm gonna change signs to everybody. It says QL divided by TL minus QH divided by TH. Okay, so if you have this, now let's just see something happening. Okay, so you have second law here, and up here you have, so this is first law, and this is a second law. And you will say, okay, so what? Well, let me just propose something. Let's just say, for the sake of it, let's just say that you want to, look at this. You want to produce the most work possible. Therefore, what you want to do, maybe you have this idea. Let's just do QL equals to 0. Okay, let's just do this, goes out. Well, that doesn't sound too bad, because if you do that, then QH, it's gonna be whatever it is, but then you're gonna have a maximum for W, so it's not a bad idea. Let me see if I can erase this without just, no, small. Nah, I thought I could just erase just that part, but let's see what happens. Oh, I did it. Well, okay, just pure dumb luck. Okay, so if you do this thing equals to 0, therefore this thing is equals to 0. So let's just say let's do QL equals to 0. So let's try to maximize the stuff if we're gonna do that. So we'll get W equals to QH, and this is just the first law. And the first law say, okay, so you wanna improve your power plant? Okay, so do not dump any low temperature heat into the ocean, okay? So that's what I'm trying to do. So you will have this. The first law says you can do whatever you want, buddy. You have W equals to QH. Now let's just do it for the second law. If we do it for the second law, we will have this. So I'm gonna put it over here. So Sgen equals to QL divided by TL. Let me just emphasize this with a 0 over there, because QL equals to 0. And therefore minus QH/TH. Now, maybe you see this, but QH goes in, that this thing is positive, divided by something that it's also positive, because temperatures in Kelvin needs to be positive if you're not studying some weird systems that actually have negative Kelvin temperatures, okay? But that's for physicists, or maybe for engineers, but later in life. Now, for this one, you have a minus over here, so you have a minus over there. Therefore, overall, you have a freaking minus. And I don't know if you remember this, but you can see this in one of our videos. But Sgen cannot be minus. That's an impossible. This thing is impossible. Okay, so you cannot do this. If you cannot do this, therefore, you cannot not dump heat into the ocean. You always need to be dumped. Some part of the whatever you got in is gonna be out of here. There is no way that you can convert all the heat that it went in into work. There must be some heat going out from the heat engine that wasn't allowed to be produced as work, okay? So there's something in physics or in the nature, or whatever you want to call it, that you cannot use all the heat that is going in into work. There's something wrong here. Why that is wrong? Well, it's not that it's wrong, but it's actually weird, because you could do this. You could actually produce all the work. You can actually convert all the work into heat. You can do that. That's one of the famous experiments made by Benjamin Thompson about vaporizing water, okay, or producing steam of water just by producing, by boring a metal cannon back in the revolutionary days of the USA. Okay, so you can actually do that. What I mean is that you can actually produce all work into heat, but not backwards, not the other way around. So it's not like a symmetric thing to do, okay? Well, that's one of the conclusions if you use first and second law. Look at the first law. The first law say, well, yeah, you wanna do that, do that. But then the second law comes in, and that's why it has, the second law has some type of, in nature, more important hierarchy in what laws are referred, okay? Well, that's my idea. You don't have to follow along those lines. It's not that the second law is more important than the first law, but it says something, maybe something more fundamental than a conservation equation over here. Well, good. So let's move on to what? Let me just do this. Oh, more about this stuff? Yeah, more about this stuff. So what I'm gonna do over here is to, let me just move it around here. How can I do this? Oh, can I do this or not? Let me just look at it. Nope. Okay, there. I just want more space here at my right. So, well, not that much space. Let me just increase that. So what I'm gonna do over here is the same thing. Oh, the same thing? Well, yeah, kind of. I'm gonna take the second law. So this is the second law, okay? This is what I have over here. And now I'm gonna do, we already have one case, right? So we have one case over here. Let me just try another, this one. Let's see what happens. Hopefully it's something better. But well, let me just try another color, maybe this one with this thickness. And so again, Sgen equals to QL minus QH divided by TH. So this is just second law, okay? So now let's do the ideal, this is horrible, ideal process. No. Okay. Let's do this. Maybe you know what I'm trying to do. Let's just do Sgen equals to 0. That is, let's just do a reversible cycle. Maybe you have heard or read about this word, reversible cycle. And let's just do this. So 0 equals QL divided by TL minus QH divided by TH. So what I will have here is that I'm gonna put QL in explicit form. So QL equals to equals to what? Equals to QH, oh my God, the H, TL divided by T. Let me just see if I can do the H right. Okay, so this is just simply a consequence of trying to use the second law when the entropy generation equals to 0. That is, I'm forcing to do the best cycle ever possible, okay? This is what I'm trying to do. And I'm gonna use this QL into the first law. So using 1 and 2, so using 1 and 2 when Sgen equals to 0. So again, this is just one case. The reversible case, I'm gonna put it over there. So W equals to QH minus QL, but instead of QL, I'm gonna put QH times TL divided by TH. Therefore, if you do some algebra, it's not very hard. QH equals to minus TL divided by TH. Okay, so W. Now, take a look at this. What I'm trying to put is this. So if you want to convert something of the work, you need to put into some of the heat, okay? That's what you need to do. And I just want to erase those guys. And therefore, you can do it. Let's just say you put 100. Let's just say you put 100 of that one. So if you put 100 of that one, then you need to multiply it times this indicator. I will tell you a name for that one. So 100. Oops, what is happening over here? Well, perhaps what is happening is my lack of proficiency with this type of tools, but okay. So you had that. Let's just assume you're putting into 100 units of heat, whichever, BTUs divided by hours, or BTUs, or kilojoules, or petajoules, whatever you want to say. So times one of the indicators, okay? So times one of the indicators, and you will have, whoops, your work, okay? So it seems that no matter how much heat you are putting, let's just say you put 100, you need to multiply this by a factor. This guy is a factor which name is the Carnot efficiency. So this thing has a name, a very important name in thermodynamics, Carnot, or something like that. I actually don't know. I'm just laughing at myself by trying that. So Carnot efficiency, this Carnot efficiency is actually this term over there. And if you do a little bit of math, you will see that this thing cannot go from here to there, okay? So it's trapped between 0 and 1, and the value actually depends on this on these values. Okay, so what you have over here is this thing. This thing will never be greater than 1 and will never be negative. Therefore, it will stay at some value within those within that range. Let's just say that I have some TL and some TH, that it will give me an efficiency of 0.7. You can actually do the math and see what happens. You can play around with TL and TH to see what will happen if you have a 0.7. It actually depends on this heat reservoir here, high temperature, and the low temperature reservoir. So it actually depends on that. But I'm just putting some numbers over there. So if you put this, you will have 100 times 0.7, okay? And this would be equal to 70. So it seems that no matter your input of heat, okay, as 100, you will always got across this guy, and you will never put more work. You can never produce more work than the heat that went in. And this is shocking, okay? And this is for the best case ever. This is for when everything is completely and absolutely perfect. So for perfection, for this perfection, you cannot attain 100. You will never produce 100 for the work. There's something always there that won't let you to do that. The only possible way to maybe take this Carnot efficiency into 1 is to have a really, really low TL and a really, really high TH. For example, let's just take this thing as, 2.7 Kelvin as outer space, and TH as the surface of the sun at 6,000 Kelvin or something like that. So you do the math, and this thing will be really, really close to 1. So if you put a heat engine between the outer space and the surface of the sun, maybe you are allowed, it doesn't seem that you're gonna do it, but you are allowed at least to attain a really close number to 1 here, a really close number to 1. But it seems that you are stuck with imperfection as because the nature is telling you it doesn't really matter what you do. Maybe if you do the most perfect case, then you still cannot achieve to take from 100 units of heat 100 units of work. This is shocking. I don't know if you have seen it, but this is if you thought about it, this is actually really depressing, because you cannot take from an energy source. You will say, I'm going to take everything from this energy source, and you will say, well, maybe I'm doing fine or something, but you cannot do it because physics is actually telling you this is impossible to do. Okay, so this is something really important to see. Well, okay, so this is just for today, okay? But remember this, we have seen here the power cycle. I did first law for this thing. Then I did a second law. This is pretty standard stuff to do first law and second law for this type of system, which is doing a cycle. Now, what I got from there, I take a look at this possibility. Let's just try to not take out any heat into the ocean or the atmosphere or something, and you will see that it's impossible. I always need to put some heat out of the heat engine. Okay, fine. And then what I'm trying to show you is that I want to take the ideal case. I can never produce the same amount of work as the amount of heat that went into the heat engine. It's impossible. Somebody is forbidding me that. And this guy is actually the Carnot efficiency. Well, Carnot efficiency, I will talk to you later about Carnot and what he did. But he was actually pretty ingenious. He was actually a genius, I think. And well, okay. So that's it for today, guys. Okay. Take care. See you.